Assalamualaikum. We will continue our lecture for Fire Explosion Part 2. Introduction, effects of fire on people, right? This is called a first degree of burn, which is a mild level causing reversible reddening, erythema, and no blisters are formed. And the skin usually revert to normal within 24 hours. I believe most of you have experienced having first degree of burns. This is the second degree of burn. You can see blisters. Okay, this is much more severe. Maybe shallow. The blister depth may be shallow with only the surface layer of skin is damaged, and it is a water inside there. Right, it's more severe cases and the whole dermis is damaged. And this is a degree of burn. Right, it's a thermal radiation effect on people depend on the length of the time, so we can just read through this. Okay, this is the overall summary of a first degree of burn, second degree, and the third degree of burn. Okay. We go on explosion. Explosion is a sudden and violent release of energy. Okay, the energy release must be sudden enough to cause local accumulation of energy at the site of location. When it comes to explosion, of course, there will be a release of energy, right? So the energy then will be dissipated by various ways, including formation of pressure wave, projectiles, thermal radiation, and acoustic energy. So how is the pressure, how the energy being converted? This is how it's being done. Okay. The damage from the explosion is caused by the dissipating of energy. So when the energy dissipate from the initial place, it will transfer from one place to another place. So that's why you can see the effect of explosion is huge. If explosion occurs in a gas, the energy causes the gas to expand rapidly. Okay, for example, this is the point where the explosion happened. So you can see the pressure will reach up to 300 meters of radius. Depends on the energy dissipated. Okay. To understand the explosion impact, you must understand the dynamic of the pressure wave. The pressure wave propagates in air called the blast wave. A shock wave or shock front result in the pressure front has an abrupt pressure change. A shock wave is expected from highly explosive materials such as TNT, trinitrotoluene. Normally, this is a benchmark of an explosion. We benchmark the TNT. Okay. The maximum pressure over ambient pressure is called the peak overpressure. This is the comparison. Right. For example, the consequences of a 1 kilo TNT blast. If this is the point of the explosion of a 1 kilogram of TNT blast, 1 meter fatalities is possible. 2.7 meter, what's the consequences? Severe contusion injuries. 11 meter, this distance from the blast rules out fatality, but minor injuries may occur. So it depends on the radius. So we need to calculate the peak wave. If we know the radius, we know how much kilogram of explosion, for example, how much kilogram of TNT, so we can determine what is the consequences of these people over here. Okay, we want to know what are the consequences right now. Okay, so parameters affecting the behavior of explosion. Number one is ambient temperature, pressure, composition of the material, physical properties, the nature of the source, for example, the type and energy of duration, the geometry of surrounding, is it confined or unconfined, and the amount of combustible material, turbulent or combustible material. There are two main, you need to distinguish between these two main things, which is detonation and deflagration. Both are explosion, right? But each of this has its own characteristic, right? So detonation and deflagration. You just read through this. Detonation reaction from propagates above sonic velocity. Deflagration, reaction propagates at a speed less than the sonic velocity, meaning that detonation is very fast, faster than deflagration. Okay, so this is a visual how you distinguish between detonation and deflagration. To make it more understand, please review this video. That's how you determine, distinguish between detonation and deflagration, right? By hitting this, you will detonate, meaning the explosion is very fast. But deflagration, the rate or kinetic, or the kinetic rate is lesser than the detonation, right? So for more info, you can just go to this link, YouTube, and you can see this more explanation how to distinguish or to differentiate between detonation and deflagration, right? Okay, a blast damage from overpressure. We need to know what is the damage from that overpressure of explosion. You can just read through this. Okay, for example, blast wave breaks windows, exterior walls blown in column by damage. For example, this is the explosion, so it will break the direction of the pressure here. However, if the direction blast wave force flow upwards, it will go upwards, so it will damage the floors. So it depends on the direction of the wave. And also it will go when blast waves surround structure. For example, it will compress the big enough to compress the building. Okay, so it can go in many ways. And about the question, how the pressure is measured as the blast wave passes? How do you measure the pressure? If the pressure transducer is at higher angles due to blast wave, the overpressure measure is called side-on overpressure, right? So we go, I'll just skip that one. So this one, I'll go straight. You can just read this. Okay, these are some damage approximation based on the overpressure. It is in table 6.9. Okay. For example, if the overpressure is 1 kilopascal, so what is the possible damage? Is a glass breakage. If it is 2.76 kilopascal, it is limited minor structural damage. So how do we calculate this overpressure? So we will go through estimation of the overpressure. Experiment with explosive have demonstrated that the overpressure can be estimated using an equivalent mass of TNT. We call it MTNT. It's the equivalent mass of TNT. And the distance from the ground zero point of the explosion, R. Even though it is not using TNT, but we can calculate it using an equivalent mass of TNT. The empirical derived scaling law is here. ZE equals to R over M TNT, 1 over 3. All right, R is the radius, and this is the equivalent mass of TNT, where ZE is the scale distance. So we want to know the ZE, right? So when you calculate the ZE by using this graph, you know the ZE, so you can calculate the PS, the scale over pressure. Okay, so you know the PS, you know the ZE, then you can calculate the scale over pressure. When you know the scale over pressure, you can calculate the peak over pressure, P naught. This is the one that we want to calculate, P naught, right? Where PS is the scale over pressure determined from the graph. P naught is the peak side on overpressure, the one that we want to determine. Okay, and PA is the ambient pressure. You can also use this equation by having the ZE, just include the value of ZE here, then you can have the PO over P naught over PA. If you don't have the graph, then you can use this equation. So we go an example. 1 kilogram of TNT is exploded. Compute the overpressure at a distance 30 meters from the explosion. So we want to know the P naught. All right. So the solution, first use the equation to calculate ZE. You know the radius is 30. The M is the kilogram, 1 kilogram of TNT. You get 30 ZE. So by using the graph, 30, 10, 20, 30, extend it here. So it will go somewhere over here. The value is here, 0.0312345.005, something like that. Right? This is table 6.9. So then from the figure, the scale over pressure is 0.055 from the graph just now. So by using the equation, 0.055 is equal to P naught over, so the ambient is 1013 kilopascal. So you get P naught equals to 0.055 times 101.3. So you get 5.6 kilopascal. Okay, so what can this overpressure do damage? So from this, you refer to this table. Okay, 5.6 kilopascal is roughly here, 0.8. Okay, minor damage to house structure, something like that. So you just suit in the most suitable. So this overpressure will cause minor damage to the house structure. All right, so this is one direct example for you to determine the peak overpressure. Right, in order for you to determine the cost or the damage to the structure or anything. All right, so we'll stop here and we'll continue further on in our next chapter. Thank you.